So up until this point in the course, we've talked about how sequences of individual numbers converge and how sequences of vectors converge. And so, of course, the next natural thing to talk about is how sequences of functions converge. It turns out that there are actually a couple of different natural ways to talk about convergence of functions, and we're going to go over a couple of them here. The first one that we're going to look at is called pointwise convergence, and it's going to mimic something that we saw when we were talking about convergence of sequences in RD. So just as a quick reminder, if we had a sequence xn that was living inside of RD, we knew the following: xn converged to another vector x in RD if and only if, for all I, xn of I converged to x of I. In other words, to check convergence of the whole vector, it was enough to check convergence of every individual coordinate. So we're going to do the same sort of thing for functions. We're going to consider a sequence of functions fn from some set A to Rm, an individual function f with the same domain and the same range, and we're going to say that fn converges to f pointwise if, well, it satisfies the analog of this condition. For every x in A, the usual limit as n goes to infinity of fn of x is equal to f of x. Okay, so this is sort of the natural thing. We have convergence of functions if we have convergence at every point, and we use sort of the same notation for that. We write fn arrow f to talk about convergence in that sense. So let's give an example of a function of a sequence of functions that converge pointwise. I'm going to set a to be the unit interval, fn of x to be x to the n. So what does those sequence of functions look like? I have 0 here, I have 1 here, I have 1 here. So f1, of course, is just the line, so it looks like that. If I want to look at f2, that is the quadratic, we're still going to start at 0, we're still going to end up at 1, but we're going to be dipping below that line everywhere in between. If I want to look at f3, that is the cubic, again we're going to hit 0, again we're going to hit 1, but we're going to be dipping even below that green line. And you can see what's going to happen here. For every n, fn of 1 is still going to be 1. But if you look at fn of x for some x strictly less than 1, then we're taking higher and higher powers of a number that's less than 1. So that's getting smaller and smaller and smaller, and eventually going to 0. So it's not too much work to check that indeed fn converges to the following function pointwise, the function f that's 0 for every x between 0 and 1, and which is 1 at x is equal to 1. So it's not too hard to check that that's true. I'm not going to go through all of the sort of epsilon delta details, but I want to notice one thing about this, which is maybe a little bit unnerving, that we had the sequence of functions fn that were uniformly continuous, and their limit f was a perfectly nice function, but it's not a continuous function. So somehow we started off with a sequence of nice functions, and we ended up with a limit object that didn't inherit the good properties of these individual functions in the sequence. That's not a wrong thing. This is a perfectly good definition to talk about pointwise convergence, but it's certainly not a very strong notion of convergence because a lot of the nice properties we'd like end up going away. Most of what we're going to do when we talk about convergence of sequences of functions is trying to come up with definitions that sort of preserve more of the character of the sequences. Okay, we'll see a little bit more about that in a minute, but first we need a bit more notation. So let's talk about, just as we have sequences of functions, we can talk about partial sums. So I'm going to consider again a sequence of functions fk, and I'm going to define Sn of x to be just this usual partial sum. And we say that this partial sum converges pointwise to a function f if the associated sum Sn converges to f. So this is exactly like what we did with sequences in series, and just as we did before, we're going to write this notation as sort of shorthand. The sum k equals 1 to infinity of fk of x is equal to f of x. Okay, so I went through that quickly, but this is exactly analogous to what we did before with sequences in series. Let's do another example, taking care of exactly the same thing that we just did. I'm going to define f sub n of x to be x to the n minus 1 for n greater than or equal to 1. I am going to define s sub n of x to be the sum from k equals 0 to n minus 1 of xk, and we know that that's equal to this formula here, 1 minus x to the n over 1 minus x. So if you look at that formula and you consider what happens for x between minus 1 and 1, not including minus 1 and 1 itself, the endpoints, we can see that all of these terms remain the same, except for this x to the n, which is going to go away, and so indeed Sn of x converges to 1 over 1 minus x pointwise. Okay? So that's probably something that's fairly familiar, right? You've seen these sorts of infinite sum formulas before, and now we have a sort of analysis class way of dealing with all of these sorts of things. All right, so that's most of the introductory definitions, but it's worthwhile to point out, as I said before, that although pointwise limits are perfectly well defined and are useful to deal with, they don't play very nicely with other properties. That is, even if my sequence fn has some nice property that I like, it might not be the case that the limiting object has the same property. So what are some examples to keep in mind when we start seeing this? Well, we can certainly have that fn is continuous and differentiable, but the limit f isn't. We can have that fn converges to f, but fn prime does not converge to f prime, even if everything has a derivative. We can have fn converging to f, but the integral of fn doesn't converge to the integral of f. So it's useful just to have some examples of this sort of somewhat pathological behavior in our back pocket when we're thinking about how convergence can go. So what are some examples? Well, we've already seen a sequence of functions fn that were continuous and differentiable, which converge to a non-continuous limit. So in particular, if fn of x is equal to x to the n, we saw that those converge to this function f of x, which was either 0 or 1. Right? And obviously, these are all uniformly continuous and differentiable, and this thing is not continuous at all. When we start looking at derivatives, things are a little bit messier. So let's talk about a sort of a funny looking example. Fn of x is equal to n inverse times sine of n to the 10x. So what does this look like? Well, if we look at this part of fn of x, that's sine of something, so it's between minus 1 and 1. We have this n inverse in front, so it's clear that fn of x is going to converge pointwise to 0. On the other hand, if you look at the derivative of fn, this huge n to the 10 term pops out front, and so you end up with fn prime is equal to n to the 9 times something. And so certainly that derivative is going to diverge, at least for many values of x. So in particular, when x is equal to 0, fn prime is equal to n to the 9, which of course does not converge to 0. All right, so that's sort of a nice little example where we can get convergence of functions fn to a differentiable function, but the derivatives do not converge in the same way. And the same thing can happen for integrals. So here's sort of the classical example. I define f sub n of x to be equal to n between for x between 1 and n, 0 and 1 over n, and 0 otherwise. So what do those functions look like? Well, f sub 1 is just 1 everywhere. F sub 2 is going to be twice as tall, but half as wide. F sub 3 is going to be 3 times as tall, but only 1/3 as wide, and so on and so forth. So if you look at f sub n of x, we're taking these rectangles, all of which have the same size, and we're squishing them inwards. And so because of the way these functions are defined, you can check that the integral of fn of x is 1. On the other hand, because fn of x is going to 0 pointwise except at 0, certainly fn of x is converging pointwise to 0. And so the integral of the limit of the fn's is 0. Okay, so this is sort of a funny thing. Fn converges pointwise to some f, and everything is integrable and sort of nice, and yet somehow the integrals don't converge. So hopefully these examples have sort of given you the flavor of the fact that you can have lots of pointwise convergence, which is going to do really funny things. You're going to not be able to preserve any of your formulas under pointwise convergence. Okay, you can preserve at least one thing, but it's not a very interesting one. So I at least should say something positive about pointwise convergence. So here's a lemma. Let's say that fn is monotone increasing for all n. So that means the fn's are sort of look like this. And fn converges pointwise to some function f, then f is monotone increasing as well. Okay, so at least something is preserved, monotonicity is preserved. How do we prove something like this? Well, it's going to be a fairly standard triangle inequality style proof, or sorry, a telescoping sum identity style proof, but let's do it again anyways. So how do we prove that f is monotone increasing? Well, we're going to fix some x less than y, and we're going to look at f of y minus f of x. So fix x less than y, and fix f epsilon greater than 0. Since fn converges to f pointwise, what that really means is that there exists some capital N, so that for all little n bigger than capital N, fn of x minus f of x and fn of y minus f of y are small compared to epsilon. In particular, I'm going to assume that I'm going to get that they're less than epsilon over 10. Okay, so that's certainly true, right? I have pointwise convergence, and so in particular, I get that these pointwise differences become small. So now I look and check to see what happens to f of y minus f of x, and I use my usual favorite telescoping sum identity to say that f of y minus f of x is bigger than fn of y minus fn of x minus these little defects, the difference between fn and f at the points x and y. So that's bigger than fn of y minus f of an x minus, I just add up this error term here twice, 2 epsilon over 10. And then I remember that fn itself is monotone increasing, and so this thing here is at least 0, and so I can remove it from the sum, and I get that f of y minus f of x is bigger than minus 2 epsilon over 10. All right, but that was true for every epsilon greater than 0, and so in particular that means that in fact f of y minus f of x must be non-negative. In other words, f of y minus f of y is in fact bigger than f of x, as desired. Okay, so we get something from pointwise convergence, we get monotonicity, but we don't get much else. In the next video, we're going to talk about other notions of convergence, and those notions of convergence are going to be a little bit stronger. They're going to be harder to satisfy, but they're going to give us more in return. Thank you.